So far we have explored about the general purpose registers SP, LR and PC, and now let's explore special registers. Okay, so there are 1 2 3 4 5 special registers. Let's first explore the program status register. Okay, the program status register you can explore from this section here. Okay, just click that and here it is. The program status register, okay, as its name indicates, it holds the status of the current execution of the program. Okay, and this is also 32-bit wide. Here you can see 0 to 31. And the interesting thing about this register is it is actually collection of 3 different registers. Okay, here it is. The program status register combines 3 sub registers. Okay, one is called as APSR, which stands for Application Program Status Register, which consumes only 5 bits, okay, out of these 32 bits, okay, inside the program status register. So you can interpret something like this. In the program status register, these 5 bits are called as APSR, interrupt program status register, that we call as IPSR, which actually consumes 0 to 8 bits here. So this is called as IPSR register. Okay, and the execution program status register, that we call as EPSR, and EPSR consumes some bits in between from here to here, that is from 26 to 25, 24 and some other bits in between. Okay, so this is collectively called as execution program status registers. So collectively these 3 registers are called as program status register. Okay, all right, so now what is the purpose of application program status register, that is APSR? So APSR contains all the conditional flags, okay, like negative flag, 0 flag. So this you might have studied in the basic microcontroller or microprocessor programming in order to detect the result, whether it is negative or whether it is 0 or any carry or borrow generation during arithmetic operation. Okay, you can make use of these flags. Okay, so these flags are actually part of application program register. Okay, if the current instruction execution resulted in any negative value in the ALU, then the negative flag will be set, and if the current operation results in 0 value in the ALU, the 0 flag will be set, and based on that you take decision in your assembly programming, isn't it? So these conditional flags will be useful when you do assembly level programming, where okay, you want to branch based on negative result, or you want to take some other decision on the 0 or non-zero condition. But if you are programming in high level languages, then we just don't care about this application program status register. Okay, so if you are interested, you can always explore this document to know more about that. Okay, now let's go to the interrupt program status register. Okay, again, this actually doesn't give any useful information, at least from the perspective of our programming. Okay, so just see what they say about this register. The IPSR contains the exception type number of the current interrupt service routine. All right, so what does that mean? It says that exception type number of the current interrupt service routine. Okay, so what we'll do is we'll understand this practically. Okay, so we already have a program where we generate the watchdog interrupt, isn't it? Right, so now let's open that. Okay, I'll just compile this and I'll just download, and okay, so I'll just go into the debug mode. So here is a place where we generate the interrupt, right? So I'll just remove this breakpoint and I'll just keep a breakpoint in the interrupt handler. Okay, great. So interrupt is triggered and we are in the handler, right, of the watchdog. You can see here we are indeed in the handler mode, isn't it? Okay, and now take a look into the XPSR. Okay, here you can see that okay, the ISR field is 16. Okay, so which actually resembles this one, ISR field. Okay, so interrupt program status register, which is actually this field. Okay, it shows that the value is 16. So that means it indicates that currently the processor is in the exception type number 16. So 16 means IRQ 0. Okay, so if I just go to my starter file, okay, and if I check the vector table, so here you can see that the IRQ0 is nothing but the watchdog handler. That means this field actually gives the information about exception type number of the currently active interrupt service routine. Great, so now let's move forward to execution program status register. Okay, so in the program status register, so you can see the EPSR actually consumes some bits in between, right? So here the T bit is very important, so which we are going to discuss next. Okay, and here it is, execution program status register. So I'll just go to the T bit, okay, which is for thumb state bit. And let's click here to understand more, and it says that the Cortex M4 processor only supports execution of instructions in thumb state. So let's discuss about the T bit of the EPSR. The first point I would like to make is, remember that various ARM processors support interworking. That means the ability to switch between ARM and thumb instruction sets in the program. If T bit of the EPSR is set, then the processor thinks that the next instruction which it about to execute is from thumb instruction set. Okay, and if T bit is reset, then processor thinks that the next instruction which it about to execute is from ARM instruction set. The Cortex M processors do not support ARM instruction set because they support thumb instruction set. Hence, the value of T bit must always be 1. Failing to maintain this during the code execution will result in usage fault exception, okay, which we'll see by doing some coding. Okay, now the bit 0 of the program counter, that is PC, is linked to this T bit. Okay, that means the PC's 0th bit and T bit are linked. Any address you place in PC must has its 0th bit as 1. This is usually taken care by the compiler, so you need not to worry about this. Okay, the programmers need not to worry about this most of the time. Okay, but if you place any address manually into the PC, then you have to make sure that whatever the address you are going to place in the PC, it has its 0th bit as 1. Okay, so because that 0th bit will be copied to the T bit. So because the PC's 0th bit and the T bit are linked. Okay, so now this is the reason why you see all vector addresses are incremented by 1 in the vector table. Okay, so this actually we saw, isn't it, in our previous lecture when we were exploring about the reset sequence of the processor, that the reset handler address is actually incremented by 1, isn't it? So this is the reason for that. So if you are unclear about these points, don't worry, we will run one sample application to understand these points. Okay, first of all, what I do is I'll just go to debug mode and I'll just reset my processor. Now the control is actually came to reset handler. The reset handler address is this one, right? Okay, you are seeing here 800,020C. Okay, so if you open the memory window and if you type the address 00000004, and you will see that this address, okay, so this is the place where you store the address of the reset handler, isn't it? So here you can see 80020C is actually stored as 80020D. That means it is incremented by 1. So when the processor fetches this address, the 0th bit will be copied to the T bit in order to tell the processor that, hey, the instructions which you are going to find in reset handler is from thumb instruction set. Okay,